Hello wonderful person, this is Anton, and today we're going to be talking about a concept of albedo. And we're going to start it right here on this beautiful moon of Saturn known as Enceladus. But can you take a guess why we are starting it here and not in another part of the solar system? I'll give you a few seconds to think about it, and welcome to What the Math. So Enceladus, as you may have already guessed, does actually have a very unusual property that is also the title of this video, albedo. It has the highest albedo in the solar system, and I'm going to explain to you what this actually means. In layman terms, it is the most reflective object that you can actually find in the solar system. Its reflectivity is 99%. It means that it actually reflects 99% of all of the electromagnetic light that is sent at it. So in other words, it's almost like a mirror. Although it doesn't really mean that you're going to see your face if you look into it, because the surface itself is very rough and very rugged, so the light will actually get scattered. But if it was very smooth, you would literally see yourself. And at first I thought it was a good idea to actually start right here on Google by typing albedo just to give you an explanation that way, but then I found this. Apparently albedo also means something else and I have no idea what this is, and I really don't even want to try to understand what's happening here. Anyway, so albedo is actually this one picture that showed up on Google, although this actually it describes it much better. So essentially, it's a reflectivity index between 0, where nothing is reflected, and 1, where everything is reflected. And then somewhere in the middle you have other stuff, like for example, grass has albedo of about 0.25, white paint is about 0.8, and a typical road in most American cities that essentially was made with asphalt would have a reflectivity of about 10%. However, in space studies, or essentially in astronomy, we can use different levels of albedo to determine different properties. Like for example, if we were to send radar waves at this asteroid Vestoid here, depending on how much radar waves we get back, depending on essentially radar reflectivity, radar albedo, we can determine how much metal is present on the surface. The more waves we get back, the more metal there is. So you can essentially determine whether something has metal or a lot of metal or doesn't have any metal by bombarding it with a lot of radar waves. On the other hand, if you were to use simple visual light, you can determine how much ice there is on the surface. So there's actually quite a lot of complex studies with albedo when it comes to various types of objects. But if you were to simply look at the average albedo, also known as bond albedo value, you could actually determine how much heat an object receives from for example, the sun or space. So let's just say we take a look at one of the most well-known objects in the universe, essentially our moon, the object that pretty much everyone sees at least once in a while. So even though it is pretty bright at night, and even though most people assume that, you know, it's a bright object, it's probably very reflective, this is actually one of the darkest or least reflective objects in our solar system. Its albedo is somewhere around 11% or 0.11. It's basically really dark. If it was brighter, if it was actually similar to, let's say, an asteroid or Enceladus, it would be ridiculously bright at night. So bright that you could most likely even read a book. But albedo actually goes a little bit further than that. As a matter of fact, it has a lot of power when it comes to making certain objects either really cold or really hot. Now this is Venus. It's known as the hottest planet in our solar system. But many people don't realize that it could potentially be much hotter. As a matter of fact, it's far from being as hot as it could be, because it has a very high albedo. Its albedo is actually close to 90%, 0.9. It reflects pretty much most of the light it gets from the sun, and a very little portion that gets through then gets trapped into its greenhouse effect. Now let's see what happens if we actually change the albedo of Venus and make it similar to one of Earth. So let's essentially turn Venus more Earth-like in its reflectivity. So here's Earth, and its albedo is currently very close to about 0.32 or 32%. I think a general value that people accept or scientists accept when it comes to Earth is around 31 to maybe just 30%, 0.3. So we're going to stick to that number. And now let's go to Venus, and let's jump into its values as well, and take a look at what its current albedo is. Now, as you can see right here, it's at around 88%, 0.88. So guess what happens if we lower it to about 0.32? So let's go ahead and type that number, and look at what happens. Insane. Almost instantly, well, practically within a few hours, the entire Venus becomes completely engulfed in fire. It's lava-like. It becomes essentially an extremely hot world with temperatures close to about 900 degrees Celsius, which is around 1600 or actually 1652, I believe, degrees Fahrenheit. Very quick calculations in my head. Anyway, so this particular object is currently very hot, and that's because its albedo has been modified to be more Earth-like. However, if we go even further and essentially turn it completely reflective, 100% reflectivity, it will actually drop by about, I guess, 100 degrees or so. So it actually became a little bit cooler. And then if you make it as dark as the moon, which is around here somewhere, it becomes even hotter, close to 1000 degrees Celsius. So albedo has a tremendously powerful effect on planets and other objects. As a matter of fact, albedo could potentially be that one tool that helps us terraform planets and also change the solar system. But unfortunately, it's not a very popular concept. As you saw from my Google search, most of the time it was an anime character that I'm not even familiar with. But let's say we do the same to Mercury. So Mercury actually doesn't have a lot of albedo. It's not very reflective. It's in a sense similar to the moon, but it is very hot. But what if we changed its albedo to make it more like, let's say, the Venus? This actually allows us to completely freeze Mercury, making it very similar to Mars in temperature. So if one day we wanted to terraform Mercury for one reason or another, all we would have to do is find a way to change its reflectivity, either by introducing some sort of aerosol in the atmosphere that reflects light, like what Venus has essentially, or by doing something even more major, like repainting the entire planet. Okay, maybe that's a little bit too much, but I think an aerosol is actually a pretty good solution. Now you may be asking yourself, well, how about Mars? Can we actually terraform Mars that way? Can we literally turn Mars super warm by making it darker? Well, Mars is already pretty dark. Mars's albedo is quite low because it's a dark red planet. It's full of various oxidized materials on the surface, and they are actually not very reflective. And I guess you can technically make it even less reflective by introducing various synthetic components, but even that will not really give it that much temperature, unfortunately. It's not really going to get much warmer. And the reason here is because, well, it is kind of far from the sun and it's not really receiving as much sunlight as Earth, Venus, or Mercury. But it will get somewhat warmer, so this could potentially be a solution as well. Now, synthetically, we've been actually able to produce some really interesting materials. Like, for example, this right here is what's known as a dielectric mirror, which is the most reflective thing you can have here on Earth. It reflects everything, practically everything. I think it's like 99.999% reflective in terms of albedo and very efficient at being what it's supposed to be, a mirror. However, these are synthesized and they're very difficult to make, so it will be difficult to produce these in large quantities. On the opposite side of the spectrum, we have this material that was actually produced in the UK, known as Vanta Black. Vanta Black is a synthesized super dark material that already has found quite a lot of purposes in, well, mostly different engineering fields, but it essentially absorbs 99.6% of all electromagnetic radiation, which means that its albedo is about 0.04. And so this makes Vanta Black the darkest material in the universe, at least as of now. We might be able to produce something even darker, but for now this is pretty dark. It's as dark as it gets. And I guess hypothetically, if we find a way to produce vast amounts of Vanta Black or some other dark material, we could maybe cover some parts of Mars with it to make it slightly warmer, but still not really that effective at creating this desperately needed warmth on the planet to make it more habitable. So anyway, that's kind of really all I wanted to show you in this video. I wanted to talk a little bit more about this very interesting effect that's not really that well known, or I guess in some sense it's not really discussed very often, but it is a very powerful property that many objects have, and they change completely, as you saw with Venus, depending on what numbers you put in there. So with very low albedo, this object becomes super hot. With very high albedo, it becomes still hot, but far from the temperatures it had before. And so hopefully now you know a little bit more about this pretty exciting concept, and in one of the future videos we'll explore this a little bit more, and we'll actually look at some other objects with some really extreme albedos. Anyway, thank you so much for watching. I'll see you guys tomorrow. Come back tomorrow to learn something else. Space out, and as always, bye bye. And maybe even consider supporting this channel on Patreon, because it does help me a lot. Anyway, so since we're almost completely destroyed Venus now, might as well finish our job by maybe detonating it and seeing what happens if you detonate a super hot Venus. Okay, kind of what I expected.